A commercial airliner's wingtip can flex upward more than 10 feet during flight. It looks like the wing is about to snap off. It isn't. Every second in the air, that wing absorbs forces heavy enough to crush a truck, and it's built to take it. So what's actually holding it together while it bends like that? Peel back the metal skin of any airplane wing, and you'll find something that looks less like an aircraft part and more like a rib cage. That's not a coincidence. Engineers call the main structure the wing box, and it's the single most important piece of the entire aircraft. Every ounce of lift the wing generates, every pound of fuel it carries, every gust of turbulence that slams into it, all of that force funnels straight into the wing box. If this structure fails, nothing else matters. So aircraft designers build it like a fortress, using 4 components working together: spars, ribs, stringers, and skin. Let's break down what each one actually does. Start with the spars, because these are the backbone of the whole wing. A spar is a long beam that runs from the base of the wing all the way out to the tip, and most modern airliners use 2 of them, a front spar and a rear spar. Picture the spars like the 2 long bones running down your forearm. They're the parts doing the heavy lifting. In flight, air pressure builds up underneath the wing and pushes it upward, while the weight of fuel and the wing structure itself pulls it back down. That constant push and pull creates something engineers call a bending moment, and the spars are built specifically to resist it. Most spars use an I-beam shape, the same cross-section you'd find in a steel beam holding up a skyscraper, because that shape resists bending better than almost any other design while keeping weight down. And here's the part that surprises people. The closer you get to where the wing meets the fuselage, the more force the spar has to handle. That's why spars are thickest at the root and taper as they stretch toward the tip. The root of the wing is fighting the combined weight and force of everything beyond it. But a spar alone can't do the whole job. Twist a long beam by itself and it'll flex sideways, which is exactly what happens to a wing when uneven air pressure hits it during a turn or a gust. That's why aircraft use 2 spars instead of 1. With a front and rear spar connected by the wing's skin, the whole structure becomes what's called a torsion box. Twisting force on one spar gets transferred to the other, and the 2 of them resist it together instead of one spar fighting it alone. This torsion box is the true core of the wing box, and it's strong enough that in most modern jets, this sealed compartment doesn't just hold structure, it holds fuel. The space between the spars becomes an integral fuel tank, meaning the wing skin itself seals in thousands of gallons of jet fuel with no separate tank required. Now here's where the wing gets its shape. Spars are strong, but they're just straight beams. They don't curve. And a wing needs that curved, teardrop profile called an airfoil to generate lift in the first place. That job belongs to the ribs. Ribs run across the wing from front to back, spaced out along its length like the rungs of a ladder, and each one is cut into that precise curved shape. Bolt a row of ribs onto the spars, and suddenly you have the outline of a wing. Ribs do more than shape the wing, though. They take the load pressing on the outer skin and stringers and funnel it inward to the spars, and they also stop the thin skin from buckling or crushing under pressure. Think of ribs like the hoops inside a barrel. Without them, the wooden slats would collapse inward the second you filled it with liquid. Ribs do the same thing for a wing skin, keeping it rigid under constant aerodynamic pressure, so spars handle bending and twisting. Ribs hold the shape and support the skin sideways. What's left? The skin itself needs help too, because a thin sheet of aluminum or composite stretched between ribs would ripple and buckle under load, especially under compression when the wing bends. That's where stringers come in. Stringers are long, thin strips that run the length of the wing, riveted or bonded directly underneath the skin, running parallel to the spars. Their job is simple but critical. Stiffen the skin so it can't wrinkle or buckle when the wing flexes. Picture corrugated cardboard. A flat sheet bends easily, but add those internal ridges, and it suddenly resists bending in that direction. Stringers do the same thing for wing skin, running underneath it like structural ribs inside cardboard, turning a flimsy sheet into a load-bearing surface. On a large commercial jet, you'll find dozens of stringers packed across a single wing, each one carrying a share of the compression and tension loads as the wing flexes through every flight. So picture the whole system working together. Air pressure pushes up on the wing. The skin and stringers pick up that pressure first and pass it to the ribs. The ribs funnel it inward to the spars, and the spars carry it all the way back to the fuselage, where it transfers into the body of the aircraft. Every piece has one job: and together they turn a thin curved shell into a structure that can flex feet upward in turbulence and snap right back into place, flight after flight, for decades. Now look out at the very tip of the wing, and you'll usually spot something curving upward, sometimes sharply angled, sometimes blending smoothly into the wing itself. That's a winglet, and unlike the spars and ribs buried inside the structure, this piece is solving a completely different problem. Not strength, but drag. Here's what's happening at the wingtip during flight. High-pressure air sitting underneath the wing is constantly trying to escape toward the low-pressure air on top. At the tip, it finally gets its chance, curling around the edge and spinning into a violent, rotating column of air called a wingtip vortex. You've probably seen it, that ghostly spiral of condensation trailing off a jet's wing on a humid day. That vortex isn't just a visual effect. It's a serious performance problem. It creates what's called induced drag, and it's powerful enough that air traffic controllers have to space aircraft minutes apart during landing. So, a small plane doesn't get flipped by the wake of a jumbo jet ahead of it. The fix for that vortex turned out to be smarter wing shape, not more wing. A winglet redirects the escaping high-pressure air before it can curl fully around the tip, weakening the vortex and cutting the induced drag that comes with it. In flight testing, this single upward bend at the wingtip has been shown to cut cruise drag by as much as 7%. Scale that across a fleet of aircraft flying millions of hours every year, and the payoff is staggering. Winglets are now standard on more than 10,000 commercial jets worldwide, and they've collectively saved over 15 billion gallons of fuel. That's not a marginal tweak. That's one curved piece of metal at the wingtip, reshaping the economics of modern aviation. So next time you're on a flight and you glance out the window and see that wingtip curving upward, or you catch the wing flexing gently as the plane climbs through turbulence, you're not looking at something fragile. You're looking at a structure engineered down to every rivet, every beam, every curve, built specifically to bend, twist, and flex without ever breaking. That flex isn't a warning sign. It's proof the design is working exactly as intended.